Hello, the purpose of this video is to cover the contents of User Story 2531, which consists of developing an improved drop-down filters user interface. The name of the student is Lester Hernandez. The project is BreazeHome 4.0. Our product owner and instructor is Dr. Masood Sajadi. Contact information is shown on screen. This user story will be described as follows. As a user, I would like to see an advanced filters user interface that includes helpful information and data such as density frequency charts, as well as other simple filter options. The whole idea behind this user story was to create a way to filter or refine the properties shown in the results page based on certain parameters. When I began working on this user story, the system at that time had a very bare-bones user interface for the filters, and it was missing a lot of elements in accordance to the design that was planned, and the functionality of most of the elements was non-existent. To provide a better idea of what this feature consists of, I will go to the BreazeHome website and show where the feature is located, as well as a brief overview of its functionalities. This is the landing page of BreazeHome. We'll go ahead and click on Browsing Properties in Miami, Florida. And here we can find the Filters drop-down button. If we click on it, it would expand the filters, which consist of sliders and some charts that are basically histograms showing the density on certain intervals of numerical filter options. We can expand the filters, we can compress them, we can completely close the filters, as well as resetting the filters. So that is basically the planned design, location, and functionality of the filters, which will directly affect the list of properties and properties shown on the map of this results page. The acceptance criteria for this user story consisted of modeling the filters UI based on a provided design. I did not come up with the design of the UI. It was provided to me, and my job was to implement the filters user interface in accordance to that design. The second point of the acceptance criteria was that applying filters displays correct filter properties list and map, which basically means that the list of properties on the results page will basically be refined or updated based on the filter selected, and the same thing will happen with the results map. Third, applying filters displays correct density charts information and counts as described in provided design. Basically, what this means is that applying a filter on one chart would dynamically update every other chart with density values taking into account the filter that has just been applied. Fourth, the user will be able to see the filter values selected for price, bedrooms, and bathrooms, since these are the most frequently used filters. And finally, the user can reset all filters. This would include an update to the filters property list and map to the default value, as well as, of course, resetting all the filter values to their default. The functionality of the whole user story can be easily described with two use cases, the first of which we can name filter results properties. The actor will be a user, which in the case of BreazeHome would be a home buyer, home renter, or an agent. Preconditions for this use case will be the user is on a desktop computer with a browser, user has a stable internet connection, user has navigated to the BreazeHome desktop website at breazehome.com, and the user has successfully navigated to the results page. The trigger for this use case will be the user opens the drop-down filter by clicking on the filters drop-down button and modifies any combination of filters, then applies the modify filter by clicking on apply filters button. And the system should respond by updating the display list of property cards to reflect selected filter values, which is what we talked about. The property list should update, updating the display properties on the map to reflect selected filter values, updating the filters values displayed as applied on the filters drop-down button. And this means that the labels for the selected values for price, bedrooms, and bathrooms should update accordingly, updating the total count of properties as well as the count of properties encompassed by each filter selection where applicable, since the filters display counts for the total number of properties contained by the intersection of all the filters selected, as well as counts for each filter dependent on the value range selected for every other applied filter. Finally, the system should update and populate the density charts for each applicable filter with correct information. That basically means that all numeric filters that have been chosen to display a density chart for a set of intervals within that filter should update accordingly once a set of filters have been applied. The second use case that provides full coverage for this user story can be called reset filter, which is a special case of the filter results property use case. In this case, the actor is the same, the user, home buyer, renter, and or agent. The preconditions are similar with the exception of one precondition that has been added, which consists of the user has successfully applied some filters, since we cannot reset the filters if none of them have been applied. The trigger for this event will consist of the user opening the filter drop-down button, clicking on the filters button. Some filters have already been modified and applied, which means that the filters are not in their default visual value. The user clicks on the filters reset button, and the system should respond by resetting all visual filter options to the default value, resetting all the display property cards on the properties list to reflect the default filter values, resetting the display properties on the map to reflect the default filter values, resetting the filter values displayed as applied on the filter drop-down button to default, which basically means that we reset the displayed selected values for price, bedrooms, and bathrooms, resetting the total count of properties as well as the count of properties encompassed by default filter values where applicable, which basically means that for all filters that display a count, it must be reset to its default. And finally, resetting and repopulating all density charts to display their default information. The following are the UML diagrams for the filters and refined search feature. This is a use case diagram with all the actors and use cases. Next, we have a sequence diagram with the whole flow of messages as part of a filter request. And finally, we have a class diagram which exemplifies the object design. I will not go into detail with any of these diagrams since I'll be going over the code of my feature and I'm trying to avoid any possible redundancy. Now we'll go ahead and provide a general overview of the actual code for the filters feature. The filter feature is implemented mainly in three different files: the results.js controller, the results.html view, and the properties.js service. All of them are located on the front end in the directory Breeze desktop. Let's go over the results.js controller and the code located there for the filters and refined search implementation. The code for the feature starts on line 175. This first part that we see starting on line 181 and extending to line 276 sets up a placeholder chart for the price per square feet filter category. We use a placeholder due to the lack of a database field for the price per square feet option. After that, we can see on line 230 that we have some list of dictionaries being declared and initiated, such as the filter types, which contain values for text labels, whether they're checked or not, and whether they're disabled or not, for all property type options. The same is true for listing type, features and amenities, and tags. The function on line 271 called isDisable is a function used to detect if a button should be non-clickable or disabled. The function showDisable message displays an option disable tooltip if a button is currently disabled, as indicated by the disable field. On line 290, we have the options dictionary. These options are used to specify the minimum, maximum, as well as other options for all the sliders using the filters. This extends all the way to line 433. On line 436, we have a block of code that is used to synchronize the values of the sliders with their corresponding drop-down buttons, which is the case for the bathrooms and the bathrooms filter options. This code extends all the way to line 515. On line 522, we have a block of code that basically takes care of the SelectAll behavior. The code is extensive because it must take into account how to keep track of what buttons have been checked, and if all have been checked, the SelectAll function would turn into deSelectAll and vice versa. This code extends all the way to line 684. Line 688 specifies the behavior to hover over a card on the list of properties. Starting on line 701, we obtain some date elements such as the current year, current date, current month, and current day, which are used on some other filters like the year built. On line 707, we specify the filter object that we will use in our feature to basically pass filters between different files and services. Starting on line 708, we set some filters to their default initial value. On line 732, we find code for the address search feature developed by Andrew. On line 754, the apply filter function starts. This function basically obtains all filter values from values set on the HTML view and sets all corresponding values on the filter object. Basically, if a filter option has been set, a field on the filter object will store its value. This is done for every possible filter that can be set. As you can see, we have code to set all possible filters, including those that are currently disabled. At the end of this function, we call the function getPropertiesByFilter, which we'll cover in a bit, and we also call processCharts, which we will also cover in a second. What these functions actually do is basically what their names imply. GetPropertiesByFilter gets a list of properties based on the filter object that is passed, and processCharts obtains all values for charts and populates them based on the filter object. On line 1041, the resetFilter function starts, which is basically a mirror of the applyFilter function, but in this case we set all values to either null or their default value if they're set initially by default. And at the end of this function, we update the properties list, passing a filter object with the default values, as well as updating the charts to their default values. On line 1194, we have the getPropertiesByFilter function. This function is called by both applyFilter and resetFilter functions. As we saw before, it is also called inside processCharts to retrieve counts for each independent interval combination. This function uses the properties service and calls the function getByFilter found in it, which is passed a filter object and current map bounds. It then asynchronously waits for a response. This response contains the results, which are the properties list, which is passed into a scope.properties, which is a properties variable. And it also returns the count of properties for the filter applied, which is returned as part of the response object. This part of the code is not related to the filters feature. It's part of the address search feature of the results page. This part of the code was also not created by me. It is part of the hide, unhide, hidden properties feature created by Ethel. After we have all the properties list, we add all these properties into the clusters of the map, and we set up some map functions in case they later need to be used. On line 1248, we have the code for the processCharts function. This function is asynchronous, so it is not blocking, and other pieces of code can be executed while we wait for responses in this function. The first thing it does is that it sets the label of the apply filter button to populating charts, and then it disables that button there, making it non-clickable. After that, we get the chart counts for the price chart. Then we get the total sum of properties to be displayed on the count of the price filter category. We normalize the chart data, and finally we populate the price chart with the normalized data. The same process is repeated for the bedrooms chart, the bathrooms chart, the year built chart, the living area chart, as well as the lot size chart. The price per square feet count is actually given a placeholder, and it is equal to the price count. Finally, we update the apply button. This basically overrides the changes that we made to the apply button at the beginning of this function, making it clickable, and it also displays the apply filter label together with the total count. The reason why we need this in a separate function is because the execution cycle of Angular will not detect changes to this variable unless another event, such as a click or closure of an UI element, actually happens. This is not ideal. We would like the apply filter button to be clickable no matter what, without the need of having an event signal the change in its behavior. On line 1302, we have the getPriceChartCounts function, which is actually called by the processCharts function right here. This function needs a filter. It backs up all the filter values before starting execution. The filter price minimum value and price maximum values to an initial interval, in this case 0 to 100k. It initiates an array to store the counts for each different interval, and then it iterates 10 times, increasing the interval by 100k on each iteration. So basically, after the first iteration of this loop, the interval will be between 100k and 200k. That way we can get counts for the 10 consecutive intervals. This conditional loop over here, what it does is prevent the execution of the loop if another chart function is actually using any of these values. This prevents race conditions and mainly two functions writing on a value at the same time, which would be write after write, making the changes executed by a function that populates a different chart obsolete and destroying all consistency within the interval value. That's why this block of conditional code is necessary. After each iteration, we request a response object using the properties service getByFilter function that we used before, and again we pass the filter object, which in this case will contain the price filter to be within the interval 0 to 100k. On the first iteration, we pass the current map bounds, again the same behavior as specified before. We will get a response, and in that response we'll pull the count for the properties that were returned. This is pushed into the array that we set up before called chart intervals. That array would store all the counts for each successive interval. Therefore, we have 10 values for the price chart. And as we said before, we increment the minimum and maximum. That way, we would then retrieve the counts for the next interval between 100 and 200k until we reach the interval 900k to 1 million. Finally, when we're done, we reset the price filter to the value that we have backed up. The other values are not needed to be reset, since that is done by the other chart functions, and we return the chart intervals array. This chart intervals array is passed into a global variable called chart data, which is then passed into a count array function, which we'll see next. After the getPriceChartCounts function, we have a getBetsChartCounts function, which is identical to this one. The only thing that changes is how many intervals we query, but it is mostly identical, the function. The same with the getBetsChartCounts, and we have a set of functions for each chart to get all the counts for each of them. After that, we have the count array function that we talked about before. This function is passed the array of all counts, and what it does is that it calculates the sum of all values in that array. This is used to display the total count for a certain filter on the filter's UI. Then we have the value normalization function on line 1574. If we go back to the process charts function, we would see that after the count array function is called, we will pass the chart data array to the value normalization function. This function basically normalizes the data within a certain range. And if we go back to it, we can see that all it does is normalize the data within values that are proportional to the range 0.3 to 0.7. All of these values are multiplied by 100 to keep consistency with the size of the chart, since 0.3 to 0.7 will be too small of values to be shown consistently on the size in pixels specified for each of the charts. And this function finally returns an array with the normalized values. I would like to take a second to say that the normalized values are actually needed, so in case a user applies a very sparse search that returns very few results, the user would not think that the chart is completely unpopulated. Instead, he would see at a minimum a value similar to 30% of 100, which would indicate that very few properties are found in that interval, but would not leave the chart completely empty, which will be quite confusing for a lot of users in case it repeats itself on many non-consecutive intervals. After that, we have on line 1601 the populate price chart function, which is called on the process charts function. This function uses the normalized array with the data counts for the price chart. It basically sets all parameters and options for the charts with configuration options to adjust to the UI that we want to represent. This is where the final population of the chart is actually done. We have a function to populate the bets chart, as well as the bathrooms charts, the year build charts, the living area charts, and the lot size chart. However, they differ on the number of bars that are actually populated on each chart, since they all have a different number of intervals to be displayed. On line 1908, we have the function that we saw before, update apply button, which is done so no event is needed to change the label and the availability of the apply button. This is called on the process charts function after all charts have been populated. And that is all for the results.js code that covers the essential functionalities of the filters feature. The last section of this filters and refined search user story video will cover the testing approach and test cases used as part of the verification for this feature. Since the test cases combinations were very significant, a manual testing approach was adopted. Automatic testing would have taken way too long. Therefore, I was advised by our instructor and product owner to perform manual testing on a selected subset of test cases. The first test case, with test case ID test apply price, consisted of applying a price filter within the range 400K to 600K. As a precondition, we defined that all other filters, properties list, and properties shown in map would have their default values. The total property count as well as the price filter property count was recorded. The expected results consisted of an update of the map and the properties list of cards in accordance to the filters applied. This would imply that all properties shown would need to be within the price range selected. In addition, all density charts would need to update, except for that one of price, due to the way that the charts functionality are devised to work. Total property counts should be reduced. This makes sense since applying a filter will be more restrictive than applying none. The price filter property count will stay the same, which is implied on point number 3. And all property counts but that of price should be largely reduced. Again, this is due to the application of a filter being more restrictive than having no filter at all. The result of this test case can be summarized as follows. The properties in the list of cards and the properties shown in the map updated successfully. All properties shown were within the price range selected. All density charts updated successfully. The total property count was 224, which was significantly less than the 2116 that we had before. This satisfies condition number 4 of the expected results. The price filter property count was 2036, which satisfies condition number 5, and all other property counts were reduced. Therefore, all expected results conditions were satisfied by the actual results of the test. Therefore, the test passed. As you can see, the first test case was concerned with applying the price filter in isolation. The test approach adopted was to repeat this for every filter category that could be applied. Therefore, we continued by performing a test case on property type on isolation. The preconditions, expected results, and actual results were all similar. That test passed. Then we performed a test case for the bedrooms in isolation. After that, we applied a test case for the bathrooms in isolation. We continue with the test case for the ear built in isolation. Then we perform a test case for the living area in isolation. And finally, we perform a test case for the lot size filter option in isolation. All of these test cases passed, following the same approach explained for the first test case. The test for features and amenities was part of this isolation test case group. After all tests were performed for all filter categories in isolation, I decided to perform a test for all filter options applied at the same time. The test case ID for this was test all filters. As before, we had the map in the default initial position. No search address was specified. Total property count as before was 2116. And we set all of the following filters to the following values, including the features and amenities to pool. Finally, we pressed the Apply Filters button. The expected results included an update of the list of properties as well as the map. All properties shown had to be within the ranges of values selected for all of the filters. All density charts will need to update. The total property count should have been reduced for all filter options that had an applicable count, as well as the total property count displayed on the Apply Filter button. The actual result was in complete agreement with the expected results criteria. Therefore, the test passed. Finally, I performed one more test case. This test case was performed to verify the reset filters functionality. As preconditions, we had the map in a default initial position. No search address was specified. The following filters had previously been applied. As you can see, these filters are the same that were applied during the test all filters test case. Therefore, the reset filters test case was actually performed right after the test all filters case. The expected results included properties shown in list and map would reset to their default values. Also, all filtered visual values would need to reset to their default values. The density charts would update and reset to default values. The total property count would reset and increase to the default value, which at that point we knew it was 2116. And all property counts would largely increase and reset to default. The actual result was also in agreement with the expected results criteria, therefore the test passed. No specific integration test was performed for my feature. However, as part of the integration testing, I made sure that my feature had no conflicts with other results page features developed by other team members. And that was basically the extent of the integration testing performed. Some screenshots of the filters are actually shown below. If you would like to see a user guide or a more in-depth detailed list of shortcomings and wish lists for the filters and refined search feature, then you can go ahead and refer to the user guide and shortcomings and wish list videos created for this feature. That's all for this feature video. If you have any questions, feel free to contact me or Dr. Masood Sajadi. Thank you very much.